Hello, Dr. Larry. Thank you. I had fun with this final. Let's get started. So we started by generating data for three different distributions using the same parameters, and ultimately we're showing how these are linked. So when I calculate the means, I can show that they're 7 times the exponential, and that the gamma and the sum of exponentials have the same mean and the same variance. I know it's related to having the same moment generating function, but we didn't go into that here. Um, and with with the gamma, then we analytically come up with what the expected and the variance is, and the expected for the exponential, sum of exponential, and we match what we found empirically with our generated data. With these probabilities, I got a little confused because the z I associated with the exponential that we had just calculated, and but I think the main point here is if the probability that it's going to happen after 2 minutes when 1 minute has already elapsed uh, is is the same as the probability that it's going to happen in 1 minute. And it's that memoryless property of exponential distributions. We show it here, and the first time I have all this rationale, but basically it's this formula here. That's what we just described. And if those events are independent, then we can transform this into this. And so by calculating the probability that it happens in 1 unit of time squared, and that is the same number of it happening in 2 units of time, we've just demonstrated the memoryless property. Looking at the joint and marginal table, these 16 here are the joint probabilities, the edges, the margins, are the marginal probabilities. And in producing this table, we've just demonstrated independence, because for the probability that it's in the first z quartile being 25% times the probability that y is in the first quartile, you get 6.25%. So if we're looking for independence, we would expect all of these counts to be close to 625, and that's what we're seeing. If we were seeing some sort of pattern, then we would actually be demonstrating dependence. There's also two tests for independence between the two variables we looked at, chi-squared and Fisher-exact. Both of them showed independence. Fisher-exact is not appropriate here. There's too many records, and you really only need it if you have very few instances of one record. In part two, we looked at descriptive statistics and plots. I was most interested in the box plot of GR live area. I realized I could take the log of that and it would look much more normal. And so my big takeaway, and granted I did this after I did the model, is I should run box plots on all of my potential predictors and look at which ones are candidates for nonlinear transformations. I also took a nonlinear transformation of sale price, and look how much more normal it looks than before. Scatter plot we'll get into in the next section. Correlation matrix, I picked the two relations to sale price that were the highest correlation and the correlation closest to 0, and did hypothesis testing and determined that both of them were meaningful correlationships. Family-wise error, initially I thought that this was when one of your predictors encodes another one of your predictors, partially encodes. But no, family-wise error is when you say with 95% confidence that one of these predictors has a correlation to your target variable, and but that means you have a 5% chance of saying that it has a relationship, but it actually doesn't. Now, if you do 10 of those, then the probability that at least one of them is uh, going to have a false positive becomes much higher. So I'm not worried about that here because I only did it for two, and we're going to corroborate these later anyway, doing the regression, linear regression. So in the linear algebra section, we took the correlation matrix. The precision matrix is the inversion, and when you multiply the two together, you get the identity matrix. And so LU decomposition, why would you do it? Well, apparently you use the precision matrix to look for collinearity and to help you identify which predictors to use in your regression model. However, if you don't take the LU decomposition, you have to do so many calculations. And if you look, like, these calculations cause tiny, tiny errors. If you can reduce the number of errors, then you've helped with your model, the efficiency and consistency of your model. So we do like these LU decompositions. For this section, I ended up picking sale price. It's skewed to the right. It would be negative if it were skewed to the left. And we fit an exponential distribution to it. And then we use the lambda of that exponential distribution to generate 1,000 data points. So here's our original data, and here's our generated data. And you can tell this is a bad fit. Yes, that curve looks good, but this whole section here is not replicated here. So we know visually that this is not our data is not exponentially distributed. However, in the next session, we can analytically determine that. So we look at the 5th and 95th percentile for our generated data, and then we look at our 5th and 95th percentile for our actual data, and then using our actual data as 5th and 95th, we generate a confidence interval for the 5th and 95th. And it turns out that the generated data's 5th and 95th do not fall into our confidence interval. So we've just analytically shown that this isn't a good distribution for our data. If I were to do this again, I would take the log of sale price and try and fit a normal distribution and see whether I get better results. In the final part of the final, the most helpful thing was scaling my target variable. I got that directly from the textbook, but when it's scaled from 0 to 100, linearly, it doesn't affect the results of your model. However, it's much easier to read, specifically the residuals. You want to see that it's tightly bound, the interquartile range is tightly bound around 0. So I started out with common sense eliminations, and I started out with pair charts to get a sense of my data, but this also helped because I was able to eliminate records with a lot of missing variables. For the non-numeric, I also looked for ones that I could eliminate right away because they had a lot of missing variables, or if they didn't have unique values, street, utility, central area, you need at least 3. I started simplifying in batch. You're only supposed to take one out at a time, but we had so many, I took them out in batches. So after running the first model, all of these were ones that we wanted to get rid of. By the 4th model, I had found 7 that I wanted to get rid of, and I tried something different, predictor triage. If I remove one at a time, I was being way too cautious with this. Which one would I want to remove first? Which one had the lowest reduction in adjusted R-squared? You can compare adjusted R-squared between all of them because they all had the same number of missing values. When I looked at when I was going through and removing those records, something I noticed is that one of my variables that previously seemed significant no longer was significant. And my conclusion was that my model with so many extraneous predictors was predicting the noise in my data. And so it took poking holes and pulling one out to find that weakness. With backwards elimination, my general sense is that you want to find that inflection point between simplicity and accuracy. And so every time we remove one of these predictors, we're simplifying our model, and we want to not see a precipitous drop in adjusted R squared. So I finally got to a model I was happy with, and here you can see that it's the interquartile range is tightly bound around a median near zero. The adjusted R squared is relatively high. We don't have many missing observations excluded observations due to missing values. So I wanted to look at this data a little more closely. So I went through this pairwise plot, and I noticed that a lot of my variables that had a meaningful relationship with the sale price had a curve in it. And I did this before part 2, so I realized that I needed to do a nonlinear transformation of sale price, and you see that disappear. So I retrained the model and was able to I retrained the model, and I saw that maybe it's slightly over predicting values, but I was happy with this change. So I trained the final model, this time without the scaled sales price, and our submission failed. I had not taken into consideration missing values in my predictions. So I looked at those records with missing predictions, and it turned out almost all of them, it was because of basement quality was missing a value. So I ran another model without basement quality and compared to see that here, this is where you can see that because I no longer have it scaled, I can't compare these residual interquartile range to what I had previously. So here I've just shown the value of having that scale. But I was happy with this model, and there were only 3 missing predicted values left, and I replaced those with the median. If I were very competitive, then maybe I would have done a model that excluded just the one that was missing for them and see what we get. And when we submitted, we got a score of 0.15197. Here's our account on Kaggle where we made that submission and our score. Dr. Larry, thank you so much. I had a great class. Thank you.